Working on electronic equipment has many hazards associated with it that can cause injury and/or death. Please do not work on energized equipment unless you take proper precautions. Working on such equipment is done at your own risk and not at the prompting of information from this or any other YouTube channel. Hello and welcome back to Poor Man's Electronics Bench. Part 2 of this episode series will cover the work needed to fix my previous work, which shows I need to take more notes when doing crap like this. I will also cover powering the unit through an isolation transformer and dim bulb limiter until I am satisfied that no smoke will be released. Further testing will be shown to verify the unit's overall health, and then I will cover the work needed to make replacements for the missing test leads using RG62 low capacitance coax and doing a quality control test on my newly made leads. I hope this content is of interest and you stay on channel to view it. Okay, I'm back and I'm done playing around with all things soldering, and just to go over things, I'll give you a view of what the newly installed terminal strip pieces, parts, connections look like. I put the line cord back on with the strain relief, soldered my 2 line cord connections. I did discover that not paying attention to things like I should have, I installed the negative lead on this capacitor improperly. I wired it to the far terminal, and under further examination, the 2 far terminals on this terminal strip are riveted directly to a chassis ground, which means they go to the ground wire connection, which means I wired it up wrong, and I don't know exactly what would have happened, but I decided to, instead of plugging it in and seeing what might happen, I decided to fix my error. And then now this is the chassis connection is isolated by the new 100 kilo ohm resistor that's in place, and the new 0047 in place of the 005 capacitor. So now this guy is properly connected. I reconnected all my line cord connections into their proper places, and then the other side of the 2000 microfarad capacitor, I reconnected. I went back and reused that existing yellow wire that was connected to the other one, made a small J-hook solder joint, and covered everybody up with some new insulated sleeving. And you really have to make a J-hook connection due to the fact that this is going into the Molex plug, and I decided to leave a little more slack on the J-hook connection from the lead from the capacitor, because this was the one that was installed previously. And just doing a general checkup on things, I decided to check the general health of the capacitor that I removed using the measurement function on my Bryman. It's supposed to measure out to 2000 microfarads, and when it does measure out, it's taking time to go through things, but if you see, it's measuring quite a bit over 2000 microfarads. And usually what that means in an older capacitor is that the capacitor is starting to fail. It's got a parallel resistance or leakage to it that is undesirable leaving it in a circuit, and it will only get worse over time. So it was a good idea, I think, to go through this unit and start replacing some of these older electrolytics, or basically all of them. And when I get a working version of this meter, I will check that one for leakage and see exactly how bad it might have been. So I'm going to just go over a few more things on these units. And they've got 3 printed circuit boards involved in them. This, what could be considered the top board, is referred to as a digital board, and one of the main reasons it's called that is because it has counters, timers, latches, oscillators, and not the digital, but op amps. got a 10 meg crystal down here to keep track of things. It's got 4 electrolytics on this board that are going to need replacement attention, which I'll take care of. It's got well, it looks to be a homebrew heatsink from the factory on a TO266 or TO166 package transistor. And we'll check him out for the amount of heat that particular item might have. The front of the unit, this is called the display board. It only has one electrolytic capacitor on here. A lot of diodes, resistors, and some transistors. And then on the bottom side of the unit, we have what's called the analog board, and this one has your push button switch contacts, has your connections for some of the switching as well, and it also has all your trim pot adjustments to adjust calibrations on the unit. So that's just a little tour before going into things. And like I said, I was looking into mounting a line fuse on this, and even though like the instructions say you don't need a line fuse on it, I'm going to do it anyways. And personal choice on this unit because it claims to have protection through a thermal protection switch inside this transformer that should be self-resetting, but we don't know anything about the condition of that besides the fact that it's some 45 years old. And can you really rely on it tripping when it needs to? Can you rely on it closing back up after it cools off? We don't know any of that. So if we can keep that from even tripping to begin with, we'd probably end off being better off in the long run. So that's what I'm going to work on next. And in the interest of being semi-responsible, I've got my homebrew thin bulb current limiter hooked up to check out the health of the meter after the work that I've done on it so far. I've not installed the line fuse yet. I'm going to get to that in a little while. But I was just going to go over seeing if this guy kind of behaves okay and doesn't draw too much current after I did the work that I did. So going forward, I've got this on a 7-watt bulb limit, and I don't know if you can see the one bulb dimly glowing just from the internals on the meter itself. If I disconnect the outlet, I go from a 1.33 watt usage to a 0.97. So there is some internal leakage in this somewhere. And we're going to power it up. 7-watt bulb on the load that it has provides 63 volts on the outlet from the current limiting. So we're going to give it a 40-watter. You notice we got triple zeros on the meter, which is a good indication. We've got 114 volts on our outlet with 13 watts of power. I'm going to go to a 60-watt bulb. Take the 40 off. The 60-watt bulb gives us 118 volts at the outlet, so that's a pretty good current limiting. And as you can see, we've got indication on the LED. Doesn't look terribly bright though, so there could be some power supply shenanigans going on right now. We don't know the extent of that. So our triple zeros are on, so that means we have some good circuitry, and we have a good set on our zero trim pot on the back. I'm just going to check a couple of things here. First off, I'm going to check my leakage function. Press the button and it should give a couple of second delay, and it gives there's 2 positions on the switch for leakage. There is one for all other capacitors, which I have it set to. That measures with a limit of 99.5 microamps. And it gives us a decimal point here, so if you see our maximum value would be 99.9, and if we hit it to the large aluminum electrolytics, I believe it can go up to 10 milliamps. And it's also giving us an indication that it wants to do something, which is good. Our next thing is going to be capacitance value. Going to press the value button. It comes out to a negative 3.8, so that kind of tells us things are functioning. There's a 0 adjust on the front panel to adjust it to leads, and this is behaving like the other unit is, where right now we've got a totally open connection on our BNC. There's an oscillator apparently for the measurement system that needs to see a baseline amount of capacitance before it wants to start measuring anything. And in this case, it is not seeing it, so it doesn't give a proper value, and adjusting our lead 0 does nothing to try to get that function to work. So I'm going to get into looking up a lead, and I have a segment in the video where I've made some replacement leads, some RG62 coax, and we're going to see how well it will let me zero the replacement lead. And if you see, my value lets me come off of 0 and then go to either a negative from 0 or a close to 0 value, and I can go over as well. These particular lengths of cable should have been about 30 picofarads or 30 picofarads, depending on how you want to see it. But it worked out with all the joinery and heat shrink and everything. It worked out to a little bit of a higher value, but it's still an adjustable amount. And here is another set that I made, since I have 2 units. This one amazingly comes up to within a picofarad of the other one for being able to zero it. So, and there's another little way to make a connection on the front of this. I'll show later. If you got to the point where you just wanted to use 2 discrete wires coming off of banana 5-way posts coming off of here. I will get into that later, but for right now, it seems like it's got baseline functionality to it. As you can see, I have a varied amount of items on the bench. What this hopefully is going to accumulate itself into is a working version of a test cable for the LC53. I've done a little tinkering with the sample of a meter that I have that's working, and I have determined that about the average capacitance it likes to see on a test lead, because it's going to see some. You cannot have unless you have 2 separate leads going well into a component from the tester, which can be done, by the way, but I'll get into that later. The test lead itself is going to be a coax cable that has a capacitive value that the meter can be adjusted for to a 0 to start things out. And playing around with the meter a little bit, I noticed about a good value of that capacitance is about 30 pico or picofarads, depending how you want to say it. And one of the few types of coax that can pass on a connection at a lower capacitance is an RG62 cable. which I have a quantity of 8 feet of. And that means it's a little, it's just, well, it's about 2.5, a little over 2.5, close to 3 meters. And I found a spec sheet on that cable online, which I can give you a quick view of. And the rated capacitance for that item is, so it just has a per kilometer, nanofarads per kilometer. It's 45 nanofarads per kilometer. So we have, if you change kilometers to meters, that would be a division of 1,000. And if you change nanofarads to picofarads, that would also be a division of 1,000. So that gives you at let's say 2 meters, give or take. It's giving a little more. It's more like 2.5 meters almost, but not quite. Should be in the ballpark of 90 to 100 picofarads. So I have this capacitor tester, which is pretty good at doing lower values. I can zero this with the leads totally detached from each other. Comes up with a 0.02, 0.03, and this is fairly insulated on the far end. It's not a short. And if I connect to the length of cable that I have, comes up with 91, 90, 89, about 90 picofarads. So if I section this off into 3 separate identical lengths, I should get about 30 picofarads, give or take. So that's going to be my next attempt at doing things, is measuring this out into 3 comparable lengths, and I'll be back in a second after I do that and cut it. Somehow or other I had a boo-boo and figured out that I thought I had 8 feet of this cable. I only had 7, so I thought I was going to try to make two cables and have a third stub. Mail carrier alert, sorry about that. That other cable might be a little lower in capacitance for some reason. You want to be able to make this long enough so you can keep the meter a little bit away from whatever you're working on a bench in a fixed position, and then get to something, test to connect to it if you lift one side of the component, especially on a lower value. If it's a higher value, it doesn't make a difference. But this is still a pretty low capacitance compared to some other leads I've got. Another one handy here. This is a standard audio grade cable with the BNC, and you have connections to add different things on. And if I wanted to check the capacitance on this one quick, we're talking for about the same length of cable. It is 105 picofarads, and it's that adjustment knob on the front of the LC53 will only adjust to within a certain range of capacitance. From what I saw, about 30 was a sweet spot, but there's a possibility I can make an adjustment to get it up to 45. I think 45 was doable, because it looked like I can go have it read a positive 16 on something. If not, if this is too long, I'll have to make an attempt at shortening it, but I'll find out when I hook it up to the meter. So looking at that, the only other thing I wanted to do is just do a quick check and make sure there's no resistive faults in the cable. So we're going to go to my favorite, using a digital voltmeter that is capable of measuring nanosiemens, and checking across the leads. And this is settling down to below or about 100 gigaohms of conductance once I stop moving it around. There we go, we hit our sweet spot. So 100 gigaohms of comparative resistance as far as conductance. So that's an open lead on a cable. And then going through things, I just want to show you a few things. I'm going to be using fairly good quality components. These are cinch connectors made for RG59 or 62. The only odd thing is this says a 75 ohm BNC. Well, this cable is not 75 ohm, it is 90 something ohm according to the specifications. So not that it makes a big difference, because we're not transmitting an RF signal long length. We're just wanting for a good connection on a low capacitance signal. And these clips are sourced from Mueller. I just want to build some stuff that's a very good quality. This is Pomona test lead. You'll notice it has the white separation on the insulation on the inside. So I'm going to go through the first part of putting the BNC connector on. These are fairly easy to use, but you do need some sort of hex style crimper that will crimp this sleeve on after you get things in place. Like a slide. Don't forget, if you don't have a finished end already, don't forget you can get away with sliding this on. If your other end is finished, you have to slide it on backwards before you do your stripping. Now, stripping these is a couple of step process. You have this particular connector just has a insert for the conductor that it should lock in with. And then the second part, I'm not sure how long this is going to or should be, because the specifications for making BNC connectors, and I've had some experience with it because as a technician for AT&T, I was actually at one time certified to put BNC connectors properly onto coax cables, because part of the old Sonnet equipment that we installed required the manufacturer on site of some bulk cabling. And normally what would happen is this one pin in the connectors that we had was loose. You would crimp that on here separately. This measurement and this measurement had to be set to a standard to use with that connector. And I'm not sure how far this conductor slides up into here, but I'm pretty sure it's going to lock in on me. We're going to give it a push and see for right now. It's not going in too far, and it's definitely not locking. So what I'm going to try to do is remove some more of that. My wire stripper's handy. One nice part about this is at least it doesn't involve any heat. Take two cuts on that polyethylene insulation, one with a larger one with the other one. If you notice, this is silvered a little bit. I took a little bit of liquid tin and put it on there in lieu of tinning it with a soldering iron. So in this case, the braid should get up on there better. Okay, we got to the point where that's as far as we can go, so this doesn't really lock on there well at all. It's just going to rely on, and if you can see, there's a little gap. So what I'm going to do is just cut a little bit off of this tip, and then making sure that there's no braid interfering between the two connections. I'm going to slide the sleeve back up. where it catches all the braid. And choose the appropriate size crimp. This particular crimper is a cheap overseas sourced one, but hopefully it's going to do its job, and that should give me a good connection. And I will put a piece of heat shrink over this part of it in order to do a little strain relief and also to keep things in place a little better. Hopefully over time that it won't dwell off from its connection. So I'm going to pause and do that, and then set up for the connectors on the other end. And here's where some arts and crafts comes in for making cables. The first thing you want to do, since you're probably going to have a hard time sliding heat shrink over the end, is slide some down towards your BNC prepared end already. I put one piece that was going to give some coverage, and both of these have an internal hot melt glue adhesive to them, which is nice because they really stick on there and form some more protection. And in this case I chose to cut back about 5/8 of the outer insulation to expose some braid, and I've got a couple of reasons for that. The first off is I'm going to be able to expose a little more of the inner conductor. Tried my best to just roll over I didn't try to vigorously cut. I just rolled over this razor over that, and I still got some braids cutting loose, but in the grand scheme of things it's not going to hurt because there's never any large amounts of current going through here. Make sure that there's absolutely no outer conductor braid going anywhere. This insulation is a very delicate polyethylene with a low melting point, and it's something that you really don't want to expose much heat to. But you still want to keep it insulated from the outer shielding as much as possible. And what I'm going to do to accomplish that is I'm going to use some small silicone tubing, cut the length. I want to make a piece just long enough to leave me some uninsulated wire to go and connect, as I will show in a second. So I'm going to cut off a good majority, probably up to about a 1/2 inch of this inner insulation, and do it in 2 cuts with this particular stripper. Oh boy, okay, one more. You gotta get it on the smallest wire, and got a couple of bites on it, and I think I got it. Okay, probably zoom in a little on what I'm doing here. Now that I've got that portion of it done, I could even go a little more, because I'll show you what I'm going to try to accomplish here in a second. Making a first cut just to cut through most of the insulation, then a second cut with the smaller final gauge cutter. Trying not to nick or harm anything. I'm going to then take a piece of the silicone, probably about a little over half of the length of that exposed conductor. Slide it on here. It's funny because although these look like they have similar properties to them, the silicone will not be affected by heat. I can even go a little more in that inner conductor. I keep on making these cuts. Measure once, cut 5 times, as they say. I don't do this every day, so it's not like I'm going to do it right on the first shot. Okay, so that's what we have. That is probably about a little over a ½ inch. That must have been like about a 3/4 amount of braid I exposed. That's a little over a ½ inch there. And I cut a small piece of silicone, so I'm going to put that on here. When I'm soldering this braid, it's also going to apply some heat to the polyethylene jacket in there. So what I'd like to be able to do is cut open my sheathing for about a 1/4 inch or so. What that does is it allows for some expansion. And then I saw one person, Mr. Carlson, make a cable like this. He inserted a piece of tubing, Teflon tubing he had, that was large enough to go into things. But what I'm going to do instead is I have this Nomex paper left over from a bunch of other projects, and I can put that in place, and that's a good heat insulator. So now we have the chore of connecting the inner cable together. And what I'm going to do is put some flux on this guy, and then I'm going to try a little something similar to what Mr. Carlson did, except with a twist. I'm going to take one of my pieces of brass tubing that I use for connecting everything, try to get all of these strands in here, which I did. Amazing, I got it. And then I'm going to push this center conductor inside here, and it'll also go a little bit into the lead itself. And I really like a process like this because I am a big fan of a secure mechanical connection when you're doing soldering. I don't think that tack soldering is ever a good idea for a permanent connection. Something in this case, the better you can get your connection. In fact, I can even cut that silicone down a little more just to get that center conductor in a little bit. Should go to a manual focus, but then I'd have to make sure I'm holding things right at the right spot. So I'm going to go just a little shorter on that, push this down all the way to my polyethylene. And this way I can go, and that center conductor will go into the insulation just a little bit more. I do like this idea in general as far as giving a good straight connection on a wire. And it looks like it's going with a little bit of resistance. And what I can do, if I can hold that in place and give it a squeeze, and then I wish I had my other solder, my self-heating solder gun available, but I don't right now. I do have another iron heating up though. I'll have to get it into position. My old bench Heathkit guy. Whoa, sorry about that. Where are we at here? Here we are. Okay, clean the tip off on him. That's one thing unique about this iron, is that the way this stand is built, you can makes a nice third hand. dwell time with the solder. Huh. Looks like my center conductor might have went off angle and went outside the crimp, but it's really not a big deal. I have a good mechanical connection and do have some solder straight up into it. I made an attempt and failed this time. I'm not going to bother to rework it though. So I do have a piece of red glue infused heat shrink to go over that portion. Could even pull it down here a little bit. It's a very well insulated joint. And then the next part of the project is to centralize enough of this braid to make a connection to the black lead. And that will heat up a bit when it's, or it will heat up a lot actually. So I need to strip a portion of my black wire. And use oh boy, use a little flux. Okay. And I have to get a little bit better lead prep here. I would say that's pretty good. A nice little mechanical connection there. And apply some solder. You apply enough heat to make sure you see it wicking into the braid, and then you've got a good joint. And it looks pretty good. So that one can also get a piece of heat shrink. And yeah, I know I have some errant braids there. It's not perfect, but in the long run, it's going to perform just fine. You can always trim those off quickly. No harm, no foul, because they're well insulated from the inner conductor. And if I straighten them out, I actually have a good lead length. I cut these about 3.5 inches exactly on both parts, and then this is where my, just in case things got a little big for some reason, that I slid those other two heat shrinks on there, but at least I know I have them available regardless of what happened. I just have to get the smaller one slid down the cable first. There we go. The original manufacturer, I'm going to try to get a little adhesive there and there, and the original manufacturer leads are joined and then encased in a plastic resin from the manufacturer. It looks very professional. This one will look acceptable. Give it some good heat and make sure you see some of that glue flow around. And then the final, one more piece over everybody. It's nice to see that little bit of that heat shrink glue oozing out. So I'm going to let this cool down for a little bit, and then I'm going to take a look at the process for gluing or for soldering one of those Pomona or Mueller leads onto the end of the cable here. So I'll be back in a little bit. I ran into a little bummer of a modification already. First thing you find out is your entrance size for the cable for the Mueller clip is nowhere near as big as it needs to be for the Pomona cable. So I've got a small drill bit here, a 5/32 that looks to be the right size, and I'm just going to exercise drilling this out by hand. Such a thin small piece of plastic, it's not worth trying to use any power tools with it, so I'm going to do a little work at doing this, and I'll get back to you in a minute. Okay, what I did is I had a drill bit set with different size bits, and I worked my way up from a 7/64 all the way up to the 5/32 using a, that's upside down, using all 4 bits. And just doing it by hand, and that seemed to get me where I needed to go. I got the wire into there without much effort now, but a little bit of a problem getting it straightened out, so you're going to need some needle nose. Try to get in there and get a yank on it. A little problematic because the opening in the bottom restricts your the amount your needle nose can spread out to grab something as well. So think I got a good, just about there. Oh boy. There we go. I guess once you get it to make the turn, you can go through in a push. And then after that, it's just a solder joint onto the top of one of these. So I'm going to perpetrate that off camera, and then do the other lead, and then I'll have hopefully I have a working test lead to use. I can hook it up quick to my coverless meter and see how it behaves. So if you want to see that, please stand by. Well, I lost a little footage getting things put back together. I did want to show you that there's a little solder connection that needs to be made inside, and then you'll need to make a little removal of some solder and excess wire. Maybe I can show you here. You can see the wire I've got soldered in, and it's got a good joint on the inside. Zoom in and focus there. It's got a really nice joint on the inside, and the outside you're going to have a little wire stick out. And what I did is I took a pair of flush cut cutters before I pushed this piece on there and cut that as flush as possible, because if not, it's going to interfere with the ability for you to put the slightest cap on. And then getting the cap on, it's a good idea to grab it with a pair of needle nose and get a start to everything. Pull on your wire a little bit as you go. And you're going to get to a certain point where it's just going to be brute force and pushing the top in and pulling your wire lead out a little. When you're done, hopefully you'll get both of these to seat as well and equally as possible. This one probably can use a little more of a push. There, those are pretty equal. You can tell that they just got barely a little bit of that slat. And you might find out that your end gets out of alignment a little bit and doesn't retract all the way. So you can always just take a pair of needle nose pliers and line that back up. I had to do that with the red one, but that looks to be it. That's the finished product with the end on it. Some may think that the hot melt glue is a little unsightly. You can always peel it off after it cools, but should give a durable cable. And just to double check what the capacitance might be on it. And now that I have completed the production of the two test leads for the two different units, I'm going to go through the quality control portion of the video just to test and ensure that these were in good shape when finished. And I have my giga-ohm leakage tester in order to start the festivities off with. Got it set on the most sensitive indicator setting, and as you can see, just slightly touching the silicone boots is giving an indication of some conductance or resistive value. I'm going to check out the red corded lead first, the red color coded, red heat shrunk, whatever you want to call it. And it has no indication of any type of short or conductance between the two leads. And to verify that I've got a good connection, I can test the end of the connector, the BNC connector, and get an indication of continuity. So the red one looks good, so we're going to move on to the one with the black heat shrink. silicone clip leads are slippery on the inside, and you go to squeeze them open and they just spin around. Now this one has the same indication of not having any leakage, and it can show that I have continuity by touching the end. So we're doing pretty good for check number 1 out to about 50 gigaohms. And to kind of verify that the production went well, I can also bring in a quantitative measurement device. The Bryman 869S has a function for measuring nanosiemens, and an indicated value of 0.01 nanosiemens would equate to a resistance across conductors of 10 gigohms. So checking the leads with the black heat shrink on them. You can see we get a 0 out of that, and then also if I put my finger on the end, we'll get an indicated value. So that's well above any measurement a regular ohm meter can make on a digital multimeter. And this is the cord with the red heat shrink. And it's settling down to what equates to over 10 gigaohms of open circuit resistance, and touching my finger on the end shows continuity. So we can get this one out of the way, and now we're going to go into the process of measuring the capacitance on the leads, keeping in mind that these have to be lower in value compared to some of the regular BNC to test clip leads that are on the market in order for the meter to calibrate and operate properly. And I have 2 capacitance testers. I have this one, which seems to do fairly well on lower value readings. I'm going to sharpen my leads out to get any stray DC voltage that might have been stored on them. Off the leads, to a 0. And you got something that comes up kind of like a 0. It's probably going to be accurate to within 0.1 picofarads. And trying to keep the leads from coming in contact with each other as much as possible. This is coming up with about a 49.3. To write that down, it's a bouncing reading. 49.3, 49.4. Let's see, about 49.4 on the black one. Oh, also I have to short these leads out for a little bit. I found that this meter is very sensitive to voltages, even down to the point of got a negative 1 pico on the. I'm going to recalibrate this guy again. Keeps on wanting to go negative on me. I don't know why. That previous value might be off about a half a picofarad. It's not a huge deal breaker. And the one with the red insulation has a value of about 49.7. Give or take. Floats a little bit. And the last tester I have to check things with is one that I don't use too often, but it's fun to use. Got this as an auction site purchase a while back. It is a Leader Electronics model LCR740. It is a fairly accurate piece of test gear. It can do resistance, capacitance, and inductance, and it tests by using a 1000 Hertz oscillator, putting the measured component in circuit with the bridge, and then you have a compensator for the oscillator here, and then something to got a calibrated resistance potentiometer to measure the values. So first off, we're going to start off by getting this thing to set at 0. It's not an exact 0 when you turn it on. Let's see, I'll show you. Right now we're set for 100, 9.999 would be 100 picofarads on this. And this switch is set to compensate, to add a value to it. It aids an adjustment to figure out whether you're going the right way when making your compensations on things. Now we're going to go and just check the 0 on this. So I have to get the meter to indicate a null. So first off, I have to raise my sensitivity. And then to change the oscillator setting, you can see there's a slight, very slight motion in the meter indication. We have about a 7.2 about is the null, and you don't really worry about the value on this. You just need to set a null, and then you can start to change your value on the calibrated potentiometer, and then go back and again set your null using this guy, and then you can raise your sensitivity. Right now this knob is up all the way. So we have a null for an open circuit on this meter at about a 0.025 or so. So that's 2.5 picofarads added onto whatever reading I get. So I'm going to try the black heat shrunk set of leads first. If you notice this meter pegged, I got to go down to sensitivity, and I got to start looking for a null. Changing my, I'll get that in view a little better. Changing my value on the resistor, and if you notice I get a null about right there. So at this point I can turn my sensitivity up and then adjust for the compensation. And it changes and lowers it a little bit, and then this guy is so sensitive that just touching the chassis on it imparts a little more of a reading onto the oscillator. So I'll try to avoid that while making these measurements. And every step of the way you just want to go for the best null possible. That's about it for the, that's about as good as I can get, and we have about a 0.535 or so. So that would measure out to about a 0.51. So that agrees within 2 picofarads of the other meter, which is fairly close. Go for the red cord. Seeing that they both measured out in the mid 49 range. I'm going to up my sensitivity again, since the value shouldn't be off by too much. Try to go for a good null with the compensator. And then this one has just got a slightly higher capacitance value. I got things nulled out as well as I can, and that one comes up with about a 0.545. So it's within 1 picofarad of the other leads. So seems like I have done good. So we'll go on to more work on the LC53s themselves coming up next. And I have a good news day, because after all that work for making these leads, this seems to be long enough where I can put this on the backside of a bench, hopefully on a shelf, and then connect it to things. I can zero the leads quite easily using the value adjustment knob. Get right to a 0, and getting into the negative, it seems like there's a certain value of probably at least 20 picofarads that needs to be connected to the front of this meter for that oscillator to start, the internal oscillator to start working to make the measurement. If not, you get a negative value of 2.2, and it won't go or show any lower than that. But once you get a value high enough to get that oscillator to start to work, then, which this cord is, then you can apply a 0 range to things. And apparently the cord's been manufactured fairly well, because I can, whoops, took my finger off the button. Well, let's see, moving. Probably have to get a 0 value in whatever position it's in. Then I'm going to hold that down, and then moving the cord around makes the value change a little bit. If you're trying to read such a small value of capacitance, it's probably best that you use something, or zero it when you get it close to the item and then connect it if you're going to leave things in a piece of equipment. But other than that, I'm pretty happy with the results from how the leads came out. Doesn't look any worse than any of the offerings that were made online for sale on eBay as far as aftermarket manufacturers, and I know exactly how mine was made and what type of components were used to make it with, and the quality of all the work, which I can't say about anybody else's builds because they're not disclosing it in a video. So we're going to go on to more work on this unit in the next parts of this part. And my adjustment knob wasn't anywhere near an extreme in order to get the lead 0 on this, so that's a good indication. I'm just doing some general checking here. There's a couple of component values that, components that I know are heat generators. But at this point, I'd say that this unit is functional enough right now to not worry about going through further calibration until I do some capacitor replacement, which I have the capacitors for. Oh, the only other thing I'd like to check is my voltage, my DC voltage testing on the capacitors. We can do that. Got the Bryman meter handy and in range here. What I'll do is, the large scale is set for DC volts. Hook up some test leads, and just to verify that the high voltage section is working for our leakage. there's a calibration for the milliamp microamp meter in here as well, and I'll get into adjusting that, calibrating that. I calibrated the other unit fairly well. Right now this is set to 3 volts. Got 2.8 on the output. There's a little AC component to it. The top range in here, let me light this meter up here. There we go. This is 3 volts, 6 volts, 10 volts, a little low in the 10 volt range, but if you notice it has a little AC component to it. 15 volts is a little low, but again there's a AC component that's coming up in voltage. 25 volts. Here's where we can do something that I was threatening to do before, is check the leakage on my capacitor that I removed off of here. I've got our 2000 to 25 and we are set at the 25 volt range, so might as well. Coming up, I will look at what it gives for a baseline leakage value after I check it for a bit. Looks like about 720 because it's bouncing right around that value. One could say it's actually coming up in value every now and then. And out of... Oh, one thing I want to check and make sure is that this device has the resistive discharge function working properly. There should be at least a 500 ohm resistor across the terminal connections. After you release the leakage button and with no capacitive value. Got 24 ohms, so it's less than that. It might be two 25 ohm resistors in parallel, I think. Two higher wattage 50 ohms, I mean, in parallel. So that part should be working, so let's go back to checking capacitance. If you remember, this capacitor measured 2,700 microfarads and it has a marked value of 2,000. This meter says it is coming up as a 2870, so between a leakage of 800 milliamps, which I can verify on the chart, and a higher capacitive value, one would think that this one was ready for the scrap heap. Oh, and then getting back to checking voltages. Okay, we check 25. There's a warning indicator once you get up to 50 volts. Whoops. Let's get the meter in a proper setting here. Okay, AC and DC volts. So we've got 16 with a 17 volt AC component on it. Whoops. Got to change the other switch there. This is 34 volts with a 35 volt component for 100. So what it's doing is it is putting a fair amount of AC voltage through. That 200 volts has a DC with an AC modulating component. 300 volts is a 51 volts of AC and 52 of DC. .400 volts is 147 of DC and 141 of DC and 147 of AC. 500 volts. 600 volts. So that is, if you add up the AC and the DC component, that adds up to about 600. And I'm curious to see how all that filters out if I put a higher value electrolytic on it. And I'm not going to higher value, higher voltage. I'm not going to play around with it now. Because I won't get other things accomplished that I need to. But it does let me know that it is achieving an output. And I've tested nothing on the inductance side yet. There's a lead fuse. To zero it out, you should be able to short the leads and get a 0 reading on value. And adjust for that 0 as well. And it looks like that is functional. So that's a quick check on the meter's health, and for the most part it is behaving like it's supposed to. So I'm going to get into some of the disassembly it's going to take to do a capacitor upgrade and replacement on the unit. Next. Since this video is over an hour long, I'm going to call an end to part 2 and continue my work on the LC53 unit number 1 on part 3, which will involve doing some disassembly and replacing the capacitors on it. So if you're interested in that content, please look out for the next part, and if you haven't subscribed yet, please subscribe so you will be notified when that video becomes available. I thank you for viewing this one, and I hope that you tune in for the next one. This content is available on YouTube and Odyssey.com. If you enjoyed this, please like and subscribe. Hope you return soon.